All right, BNS 210, good morning. Today I'm going to talk about post-hoc tests, which you guys are already somewhat familiar with because of the worksheets. So this PowerPoint here shouldn't actually be very long, so that's good. Let's go ahead and get started. Okay, so we've talked about this equation with the F value and how it is the sums of squares between divided by the degrees of freedom between, and the sums of squares within divided by the degrees of freedom within. So in order for an F to be significant, you have to have the numerator be larger than the denominator. So basically the F needs to be greater than 1. The further away, the larger the F is, the more likely it is to be significant. So if the F is less than 1, that means that your sums of squares within, your error is greater, your random error is greater than the difference between your manipulation. So here are just some suggestions. These are things that we've already talked about and ways that you can make your within groups sums of squares smaller. And this is, of course, by eliminating your random error, because this is due to random error. So if you have a larger degrees of freedom within, that's because of your subjects, right? That's where your subjects come from. So you could have larger degrees of freedom, and that could happen. Having more subjects will make that random error smaller. Individual variation, you can consider that, a random assignment, these types of things, and of course reducing your measurement errors. All things that will reduce your random error are things that are important to make your within sums of squares smaller. And then of course you want to make your between sums of squares bigger. So this is by eliminating your confounds, by making your make sure that you have really good operational definitions, that your independent variable is very strong, and of course through also eliminating random error as well. Okay, so we've already talked about single factor multi-level designs, which is a one-way ANOVA, and then we talked about factorial designs, and we talked about the types of ANOVAs, whether we have a two-way or a three-way ANOVA. So here for our example to talk about the post-hoc tests, we're going to use our traditional caffeine and reaction time test that we've done already. This is a 3-level, this is a single factor multi-level one-way ANOVA. And you can see down here I have our null hypothesis and our H1 or our experimental alternative hypothesis. Okay, so this is our a priori prediction, this hypothesis, right? Remember your a priori versus your post hoc explanations. So this is the most convincing. Most of you guys got this correct on the midterm whenever I asked you what the differences between an a priori and a post hoc hypothesis was, and that the a priori is the better one because it is based on actual data. So this is more convincing. This is what is in support of your theory. So we've talked about post hoc predictions, and post hoc predictions are whenever your data does not quite match your a priori prediction. So instead you explain what happened based on the data that you got, and you try and explain it. So this is a post hoc explanation. This is explaining the data. This is speculative. This is just saying, well, maybe this happened. Well, maybe that happened. So you're looking for something with the post hoc prediction. So although that your data might suggest that you do have something and it's different than your analysis, you need to be careful. Your theory, okay, whatever your a priori hypothesis is, this is what should drive what tests you use on your data. So when we're about to talk about post hoc tests should already be planned. They're planned comparisons. These are things that you plan based on your a priori prediction. A post hoc test is a test you've done after the fact. So the overall ANOVA needs to be significant, and then you could look and see which levels are significant from which levels. So a post hoc test is after the fact, after a significant ANOVA. A post hoc explanation is whenever you're speculating on your data. So these are very different things. So a post hoc test should be planned because you should expect your caffeine to be faster than your decaf, which should be faster than your water, for example. Okay, so here's just an example. This is a real example from an experiment that I had. So here you see this is the ANOVA. Okay, so this is between the independent variable of a D2 antagonist that I was using on my birds. And so the dependent variable here is average, the mean locomotor activity of these birds on these different doses of D2 antagonist. So here's the ANOVA for this independent variable, and you can see here that it is significant. Okay, yay. So here's our significance. So therefore, because it's significant, I can look and see what are the differences between my levels. I have a 3-level design here. I have saline and then 2 different doses of the D2 antagonist. So you can see down here, this is my independent variable, and you can see here that these are my means between the groups. Now, I have a significant ANOVA, and so I can make some assumptions based on the means. I could say, well, it looks like saline had a greater locomotor activity than both of my aticulopide groups, but I really don't know. I don't know, statistically speaking, whether saline is significantly greater than these other groups. And I don't know, is there a significant difference between the 2 different doses of aticulopide? Just looking at the means, it wouldn't look like there would be, but we don't know until we run the tests. So if you have planned for this to happen, you could run t-tests. Finally time for coffee. You could run t-tests on these ones that you have planned. So you could run a t-test. Remember, you can only test 2 levels in a t-test. So you could say, okay, I'll just put my saline against my low dose of aticulopide, and then I'll put saline against my high dose of aticulopide, and then I'll test my 2 doses of aticulopide. You do run the risk of inflating your type 1 error rate here, keeping in mind that your ANOVA is already significant. So this is technically okay if you've already planned for it, but no worries, because we do have post-hoc tests to help you for that. And you can just click these, as you already know, in SPSS. So LSD, this is the Fisher's least significant difference. This one does not make any adjustments to the data. So this one does not account for type 1 error rate. So this is the one that you're most likely to get significance on. And this is just like a t-test. This is basically a post-hoc test that is a t-test. It's multiple t-tests. And again, it doesn't make any adjustments for the possibility of inflating your type 1 error. So here's what this looks like in SPSS. You have saline being compared to each level. Oh, I added a level here. Anyway, this is different data. Sorry. So you have saline compared to these levels, and you can see the significance between each one here. This is different data. So it doesn't look like we have any significance here. Okay, so then we have Tukey's honestly significant difference, or the Tukey HSD. This is probably the most popular test. It's called honest because it does adjust for these multiple comparisons. It does consider that you're running multiple different things, and so it does consider the type 1 error inflation that you might get had you just run regular t-test or done the Fisher's LSD test. Multiple comparisons are also called a family-wise error. This makes sense if you think about the levels of the independent variable being sort of like a family, like these are the siblings that are part of the greater independent variable, which is say the last name or something like that. So this is the family-wise error rate, and that as you compare these, you're inflating your type 1 error. So the Tukey's test does have a calculation. It considers the means in terms of the standard error. Again, you don't have to know the calculation, but that's what it's doing. So this is kind of like a fancy t-test. Again, it does consider the type 1 error rate. There's just a trick. You could only use the Tukey test when your groups are even. So what I mean by that is whenever you have equal numbers of participants in each of your groups. So if we go back here to this example, I could run a Tukey's on this because I have equal participants, equal number of participants. That's what your N is for, of course. Equal number of participants in each of these groups. So that's the only trick. If you have uneven groups, you can't do a Tukey's test. So you can only do it when your groups are equal. So let's say your groups aren't equal because you had some jerk that didn't show up to your test and stopped showing up. Well, that's what the Bonferroni correction is for. This is another post-hoc test that's really popular. And this one also tests for the type 1 error inflation that might happen with multiple t-tests. So whenever you're doing this, whenever you're doing multiple tests and you're increasing your type 1 error rate, another word for this is multiplicity. So Bonferroni is a good one for this. There's lots of funny memes on this. Okay, so this is the equation that Bonferroni does. Again, you don't have to know this, but this is what it's doing. So it takes your alpha rate, which is normally, 0.05. This is your p-value, and it multiplies it by the number of comparisons. So let's say you have 3 levels of your independent variable. It would take the 0.05 and it would divide it by 3. So therefore, in order for something to be significant, it has to be at least this level or lower of significance. So it adjusts for that multiple comparisons to like ratchet down your type 1 error. Okay, so that's it. So those are the post-hoc tests. So be familiar with the Fisher's LSD, the Tukey's honestly significant difference, and the Bonferroni correction. On the next PowerPoint, which I hope I'll have up by tomorrow morning, hopefully I'll do it tonight, is on the effect size, and then we'll do power and confidence intervals. And then I think we're done with the semester. So those are the last things I'm gonna record. So thank you for watching. See you guys. Hope you have a great day. Cheers. I got my Center College mug thinking of you all.